In this video, we will analyze the waveforms for the modulated signals in angle modulations, in phase and frequency modulations. We will start with an example for a phase modulation where the phase deviation constant is 1/4 of a period, 1/4 of 2 times pi. In angle modulations, the argument of the carrier can be written in this way: a frequency term and then phi of t, where we have the information that we are going to transmit. For a phase modulation, this term phi of t is proportional to the modulating signal. It's just the phase deviation constant kp times the modulating signal. If we compare the modulated signal in blue with the carrier, we can see that now in the carrier we have cyclic crosses at zero. We have a constant frequency, a constant phase. However, the modulated signal will have crosses at zero at different distances. In other words, sometimes the modulated signal will be ahead of the carrier and sometimes the modulated signal will be behind the carrier. Something similar happens for a frequency modulation. Here we have the same modulating signal. Now for a frequency modulation, the argument is written in the same way, but now the term phi of t is not proportional to the modulating signal, but to the integral of the modulating signal. And the proportionality constant is 2 times pi, the frequency deviation constant kf. In this case, kf is again 1/4 of 2 times pi. Again, we can see that the modulated signal here in blue sometimes is ahead of the carrier and sometimes is behind the carrier. To better understand the waveforms of phase and frequency modulations, it is convenient to remember the effect of a time offset in general in a signal and in particular in a sinusoid. If we have here a sinusoid, a carrier with a constant frequency and with a zero phase, a cosine in this case, if now we add a given phase in the argument of the cosine, in this case plus half of pi, the new signal has been shifted to the left side, is ahead of the carrier. However, if we subtract the same amount in the argument of the cosine, we have a delay of the modulated signal. Here, the signal in blue. Now, the blue signal is behind the carrier. So, positive phases will produce a negative delay. The blue signal will be ahead of the carrier, and negative phases here will produce a delay. The blue signal will be behind the carrier. Taking this into account and taking also into account that for a phase modulation, the phase that we have here is proportional to the modulating signal, when the modulating signal is positive, we will have a positive argument here. We have a negative delay. So in this case, the modulated signal will be ahead of the carrier. However, if the modulating signal in some interval is negative, this means that the term that we have here in this phase is negative, and we have a delay of the modulating signal with respect to the carrier. Here, we can see that the modulated signal is behind the carrier, is delayed. Obviously, when m of t is 0 or very close to 0, we can see that there is no difference between the carrier and the modulated signal. Summarizing, the modulated signal is ahead or behind of the carrier depending on the sign of the modulating signal. Positive sign means that the modulated signal is ahead of the carrier. Negative sign means that the modulated signal is behind the carrier. In the case of a frequency modulation, the term phi of t is not proportional to the modulating signal, but to its integral. And this means that the modulated signal is ahead or behind the carrier. But to be ahead or to be behind will not depend on the sign of m of t, but will depend on the sign of the integral of the modulating signal. When this integral is positive, this term will be positive and we will have a negative delay. The signal will be shifted to the left side. The modulated signal will be ahead of the carrier function. When the integral of the modulating signal is negative, now this term is negative, the modulated signal is delayed, is behind the carrier in this case. And obviously, when the integral is 0 or very close to 0, we cannot distinguish the carrier and the modulated signal. Summarizing, the position of the modulated signal with respect to the carrier depends on the sign of phi of t. For a PIM, this sign is equal to the sign of the modulating signal, and in a frequency modulation, the sign of phi of t is given by the sign not of m of t, but is the sign of the integral of m of t.